Today, we're going to delve into one of the most frequently asked questions within the scientific, astronomical, and curious online communities in recent months. What will happen when the interstellar object known as 3I Atlas approaches Earth? You may have come across alarming headlines, viral videos, or comments that blur the lines between science and fiction. However, today we will focus on what is verifiable, reasonable, and what we can truly expect based on data and studies. This object has sparked immense interest, not because it poses a direct threat, but because it could provide us with an almost unparalleled opportunity in our era. The chance to closely observe a visitor from beyond our solar system, something that just a few years ago was still considered science fiction. Before we delve deeper into the analysis, we need to clarify something essential. When 3I Atlas reaches its closest approach to Earth, it will be at an approximate distance of 270 million kilometers, which is around 1.8 astronomical units. To better understand this distance, let's remember that 1 astronomical unit is the average distance between Earth and the Sun. Therefore, this object will still be nearly twice as far away as the Sun itself. This means it will not collide, brush against Earth's orbit, alter the atmosphere, tides, gravity, satellites, or the magnetosphere. It poses no threat to the Earth, its climate, or any living beings. So, if there is no danger, the logical question arises: why is there so much interest, and what is truly significant about this approach? Let's break it down, step by step. 3I Atlas was detected on July 1st, 2025, by the Atlas tracking system in Chile. From the moment its trajectory was calculated, it became clear that it did not come from the asteroid belt, the icy fringes of the Oort cloud, or any established region of the solar system. Its orbit is hyperbolic, which means it is not bound by the Sun's gravity and will never return. It is simply passing through, making it an exceptionally special object. For this reason, it was classified as the third interstellar visitor in modern history, after Oumuamua in 2017 and Borisov in 2019. Initially, it was thought to be a typical interstellar comet, showing characteristics that fit quite well: the presence of icy material, coma formation as it approached the Sun, and tail development. However, signs soon began to appear, suggesting that this object was not so conventional. Among these signals were anomalous color changes, shifting from reddish and greenish hues to a striking blue after perihelion, which does not fit the usual behavior pattern of comets. Additionally, brightness increases occurred more rapidly and intensely than expected, with indications of potential accelerations that did not align completely with purely gravitational explanations. Although these details do not imply anything extraordinary on their own, they certainly raised scientific questions. Now, let's talk about the pivotal moment, December 19th, 2025, when 3I Atlas will reach its maximum approach to Earth. On that day, it will be at a distance of 270 million kilometers. To visualize this better, let's compare some figures. The Moon is about 384,000 kilometers away from us, while Mars can come as close as around 55 million kilometers during a favorable approach. This means that 3I Atlas will pass 5 times farther than Mars does at its best opposition. Visually, this means it will not be observable with the naked eye, not even as a faint dot in the sky. It won't create any light effects or atmospheric phenomena either. Estimates suggest its brightness will not exceed magnitudes detectable without optical assistance, so it will only be visible through ground-based telescopes, advanced astronomical equipment, or specialized cameras. But here's what's intriguing. The value of this approach lies not in what we will see, but in what scientific instruments will be able to observe. During this phase, both ground-based and space telescopes will work in tandem to study its physical, thermal, and chemical behavior, as well as its evolution after passing perihelion. Science observes not just the appearance of something in an image, but how it behaves, what energy data it releases, how it reflects light, how it fragments, and how it changes over time. The key scientific objectives during this approach focus on three fundamental questions. First, to more accurately determine its actual size, as visual estimates and energy calculations are not fully aligned. Knowing the exact size of the core would help better understand its internal composition and thermal resistance. Second, to confirm whether there exists any significant non-gravitational acceleration. If this observation holds true, it could indicate more complex gas expulsion mechanisms or physical dynamics different from those seen in typical comets. Third, to study its chemical composition in depth using infrared, ultraviolet, and optical spectroscopy, which would allow us to identify whether it contains materials similar to those found in comets from our solar system, or if it presents patterns indicative of an origin in a different stellar environment. An essential point to remember is that this will be our one and only chance to study this object with maximum precision. Once it moves away, it will not return. If humanity wishes to learn about material from other stellar systems, events like these are as valuable as physical samples. Now, if you're wondering what you will notice as a spectator on the day of its approach, the answer remains the same. There will be nothing perceptible. The sky will look unchanged. There won't be any special lighting, flashes, or visual alterations. If you have a small telescope and dark sky conditions, you might see a diffuse shape, akin to a very faint comet. With astronomical cameras and long exposures, more interesting and detailed images can be captured, especially of the tail. The well-known scientist and communicator Michio Kaku recently shared this concept in an interview. When we look at the sky and see an object like 3I Atlas traversing our solar system, we are not merely observing a frozen rock. We are witnessing a messenger from deep space, one that may have traveled for millions or even billions of years, passing through regions where the physical laws might not align exactly with what we know here. Every interstellar object we detect is like a time capsule from another galactic neighborhood, potentially containing clues about how solar systems form far from our own, or even materials we have never seen on our planet. If you think about it, it's almost as though the galaxy is sending us tiny fragments of its history, and our task is to interpret them. Until recently, humanity lacked the technology to detect them, but now we can not only see them, but also study, analyze, and compare them with everything we believe we know about cosmic physics. That is the real scientific leap. Moving from awe-filled observation to methodical understanding. At this point, we can reflect inspired by the style of communicators like Michio Kaku. Imagine the solar system as a house in a very quiet and remote neighborhood of the galaxy. Throughout human history, nothing much has happened near the garden. Yet now, without warning, an unknown object crosses the entrance without stopping or announcing itself. It doesn't knock on the door. It doesn't disturb the surroundings. It doesn't interact. It simply passes by just when humanity has telescopes, sensors, and advanced algorithms capable of observing it. Its approach does not represent a threat, but rather an academic opportunity. If this object behaves like an extremely active natural comet, we will have learned more about interstellar comets. If it shows unusual behaviors that don't easily fit into established models, we may have the first indirect evidence that interstellar space contains processes yet to be understood. Two possible scenarios exist after December 19th. In the first, the data gathered aligns with cometary physics. In this case, 3I Atlas will be remembered as an unusual interstellar comet, chemically peculiar and scientifically valuable, but still categorized as a natural object. In the second scenario, anomalies may persist that require updates or expansions of our physical models. In that case, 3I Atlas will become a benchmark object for future research. Therefore, to finally answer the central question, what will happen when 3I Atlas approaches Earth? There will be no apocalyptic event, no physical changes to human life, nor dangers to the planet. What will occur is far more relevant to scientific history than to our daily lives. We will gain irreplaceable information about an object originating from another stellar system. This information may answer questions, or perhaps open new inquiries regarding the nature and evolution of the universe. We are not facing an impact event, but rather a discovery event.